Hello, George Romanic here. Today we are going to calculate trajectory of a particle that is moving on a rotating disk. This is in a way continuation of my previous video where we determined the Coriolis parameter of a rotating disk. So now we go beyond and we are interested into finding the motion of a particle on a disk that rotates. The problem is now on your screen. So, as always, we will sketch this problem. So let's say here we have this rotating disk, and the disk is rotating around this axis Z. Rotation is like so, and angular velocity of rotation is omega. Let's take this to be my x-axis. And therefore, since we are using right-handed coordinate system, the y-axis needs to be into the blackboard because x cross y needs to give me z. And somewhere here, we have a particle that is moving with velocity v. So what is the trajectory of this particle knowing that the disk is rotating? And we are given boundary conditions, or rather initial conditions, that at the beginning, which means at time t equals 0, x component of this particle, x component of the location of this particle is x0, y is y0, and the initial velocity is that u is u0 and v is v0. So these are some numbers. You can plug any numbers you want if you get this specific problem with these numbers. So this is initial condition for our problem. And this will come handy later when we start finding coefficients of our solution to differential equation that describes this. So how do we attack this problem? Well, as always, we write second Newton's law. Second Newton's law says that mass times acceleration of this particle is the sum of all forces that are acting on this particle. Now, we assume that positive z-axis is up and the x and y axis make a horizontal plane, and the motion of this particle is only in the horizontal plane, in the plane xy. So we don't have to look into vertical direction. Therefore, we don't have to consider gravity. Therefore, in the horizontal plane, there are only two forces that are contributing to the motion of this particle, and that would be centrifugal force and Coriolis force. Therefore, mass times acceleration, well, centrifugal force we know is minus m, mass of the particle, omega cross r, where omega is angular velocity of the disk and r is radius vector of this particle from the origin. And origin is in the center of the disk. And Coriolis force is negative 2m omega cross v, where v is the velocity vector of this particle. Notice that all masses cancel as usual, which is very good. And now we need to find components of these vector terms in the x and y directions. Of course, I could now skip this part because we addressed it a few times in previous videos, but for the completeness of these videos and because I love these topics so much, I will do it again. So, how do we solve this cross product? Well, first of all, we need to know what is omega in our problem. So, components of omega in our problem are 0, 0, and omega, where this omega without vector is intensity of this. Why is that? Well, that's because the axis of rotation this is perpendicular. The axis of rotation is perpendicular to the plane of the disk, and therefore omega is purely along z-axis. There are no components along x and y-axis. Components of vector v are what? Well, we said that all motion is constrained in the plane of the disk. So we have u component of velocity, which is positive in the positive x direction. We have v component of velocity, which is positive in the positive y direction. And there is no w. So if you tackle this problem, but you allow this particle, this small ball, to bounce on the disk, which can be solved, then you would have w here, but we don't have that. And lastly, components of vector r. Again, this particle is on the plane of the disk, so there is only x and y component, and there is no z component of the radius vector r. Now, when we know these components, we can solve these cross products. Let's first solve this one. So omega cross r. Omega cross r. How do you solve this? Well, we use determinant. So first row are unit vectors I, j, k, where I is in the x direction, j is in the y direction, and k is in the z direction. Second row is the first vector in the cross product, and the components are 0, 0, omega. And third row is the second vector in the cross product, and the components are x, y, and 0. And this is equal in the I direction. We have 0 minus omega y, and in the j direction, minus j, we have 0 minus omega x. And notice there is nothing in the k direction. There is 0 minus 0, which is 0. So this is solution of this cross product. But now we have to do omega cross that. So let's do that here. So omega cross r. I'm trying to save a little bit of the blackboard, as you can see, so I don't have to erase all the time. That will be equal, let's write it here, in terms of determinants. Again, first row is I, j, k. Second row, components of the first vector, 0, 0, omega. And the third row is the second vector, and second vector is here. So that would be minus omega y, and this minus will give me plus omega x, and there is no component in the z direction. Therefore, this is further equal. In the I direction, we have minus omega square x. So 0 minus omega square x minus j. Here we have 0 minus, and this minus will give me plus omega square y. And again, there is nothing in the k direction. There is 0 minus 0. Okay? So we can conclude, therefore, that this vector, but don't forget this minus over here, that this vector minus omega cross r has components that are here, this minus and this minus will give me plus omega square xi. This minus and this minus will also give me plus omega square y in the j direction. I hope you can see this. I squeezed this. Let me see if this is visible. Yeah, it's okay, it's visible. So, we determined the components of the centrifugal force in the plane of the disk. So, omega square x in the I direction plus omega square y in the j direction. Now, we need to deal with the Coriolis force. So, Coriolis force minus 2 omega cross v will be equal, again, I will use determinant over here, so I, j, k, so that's minus 2. Minus 2, determinant omega, 0, 0, omega, and v has components uv and 0, as we discussed right here. And this is further equal minus 2, that multiplies in the I direction. We have 0 minus omega v. So minus omega v minus in the j direction 0 minus omega u. And there is nothing again in the k direction, 0 minus 0. So we get that this is equal, this minus and this minus will give me plus. So it will be 2 omega v in the I direction. Minus and minus give me plus, but this minus keeps everything negative. 2 omega u in the j direction. And you will remember in previous video we actually derived this, and 2 omega is Coriolis parameter on a disk. We discussed that. So now we have components and we can rewrite this vector equation as 2 scalar equations. So we will do that here. So in the x direction, we have acceleration in the x direction, but I will write that as the second derivative of the displacement. So d second x dt squared is equal. Centrifugal force in the x direction is omega squared x, and Coriolis force in the x direction is plus 2 omega v. In the y direction, we have that d second y dt squared is equal omega squared y and Coriolis force minus 2 omega u. But of course I will here write u as dx dt, and here I will write v as dy dt. Change of position with time. And now we have this system of differential equations that we need to solve. How do you solve differential equations? Well, you read books. People before us that were overall smarter than us figured out how to solve a system like this, and we follow their lead. To solve this system, I will multiply the second equation by I, where I is imaginary unit, square root of -1. So I multiply this equation by I, and then I add these two equations. So let's see what we will get here. Another thing, in order not to keep d dt, I will introduce the following substitutions. So, second derivative will be indicated with 2 dots, first derivative with 1 dot. That's called Newton's notation. So, for example, dx dt I will write as x dot. The second x dt squared would be 2 dots. It's just easier. Okay, so notice if I multiply this with I and I add these two equations, that here I will have x 2 dots plus I times y 2 dots. That's left hand side. Equals, here I will have omega squared x plus I y. Plus 2 omega, I will have here y dot minus I x dot. Now I will introduce a substitution. I will say there is some variable q that is identically equal to x plus iy. Okay, then this term over here becomes q 2 dots equals, this becomes omega squared q. And what about this? Here we have 2 omega, but we don't have x plus iy. We have y minus ix with the dot, first derivative. So let's see how we can represent this in terms of our new variable q. Let's inspect that over here. If I say, so what would be I times q? I times q would be ix plus I squared, but I squared is -1, so it would be minus y. Okay. And therefore, you can see that if I take negative of this, that this will become negative, this will become positive, and look, this is exactly what I have here. So I can conclude that this term is minus 2 omega I times q. Or I will move everything to the left side over here. So I will get that q 2 dots but here is with the dot, plus 2 omega I q 1 dot and minus omega squared q equals 0. And now we reduced this system of two differential equations to a single differential equation, which is the second order, 2 dots, homogeneous, there is nothing on the right side, differential equation with constant coefficients. Omega is constant, 2 is constant, I is constant, but coefficients are complex. And we already had similar equation in our video on focal pendulum, if you will remember that. Okay, so how do we solve this equation? Well, to solve this equation, we seek solution in a form that Q as a function of time, because time is independent variable over here, is equal, let's say, some constant C times E to K, some variable K, new variable K, times T. So this is the general form of a solution for a second order homogeneous linear differential equation. Of course, question is, how do you know this? Well, you have to study. There is no other way. Solving differential equations is studying patterns and recognizing differential equations and then knowing how to solve them. But we already had this procedure many times in this channel, so you should be familiar with it. So if, let's call this constant C1, doesn't matter. So if we plug in this into this differential equation and here differentiate 2 times and so on, we will get what is known as a characteristic equation of this differential equation. So it will be k squared plus 2 omega I k minus omega squared equals 0. So this is a quadratic equation. Solution k12 is equal minus 2 omega I plus minus square root. This squared, that will be 4 omega I squared, but I squared, 4 omega squared I squared, but I squared is minus 1. So it will be minus 4 omega squared minus 4 this coefficient times this coefficient, so it would be plus 4 omega squared divided by 2. But notice that this is equal to 0. 4 omega squared minus 4 omega squared plus 4 omega squared, this is 0. So this ends up being, this 2 cancels with this 2, and we get that the solution is minus omega times I. So we get that the characteristic equation for this differential equation has 2 same solutions. And this is the least probable, let's say, solution for this differential equation. Now again, you have to know if the characteristic equation has 2 same solutions, then the general solution Q of t is equal constant, let's say C1 e to k, and that would be minus I omega t plus some other constant C2 times t, independent variable, times e to this k, minus I omega t. And this is the general solution for this differential equation that depends on time, of course. Now we need to find the integration coefficient constants C1 and C2. To do that, we can use our initial conditions, because if we go back to initial conditions, you will see that at t equals 0, q is equal q0, because q is x plus I y. So let's see what we will get over here. So at time t equals 0, we have q0 equals c1. When t is 0, this collapses to 1. But when t is 0, this term disappears because you're multiplying with 0. So notice, well, nothing to notice. Notice the C1 is Q0. I can do this. C1 is Q0. Okay, but we still have coefficient C2 to find. Well, to find this coefficient, we have to actually differentiate this equation with respect to time and then use this initial condition that is related to velocities. So maybe should I do that here or erase this blackboard? Well, I can differentiate here to save more space. I can perform differentiation over here. So Q dot as a function of time, so first derivative of this will be C1, but C1 is Q naught. So it would be minus I omega Q naught e to minus I omega t. That's the derivative of this exponential function. Plus C2. Now we have differentiation of a product. Well, let's first differentiate t. That would be 1 times this e to minus I omega t. And then we have plus, I keep this one, I differentiate this one, but it will be minus, because of this minus, I omega t e to minus I omega t. Okay? And now, again, at t equals 0, q dot is equal q dot 0. So that would be u0 plus iv0 in terms of q and v and velocity relationship. So here we would have q naught 0 is equal. When time is equal 0, this collapses to 1. So we will have minus I omega q naught, so this, plus C2. When t is equal to 0, this term will disappear and only this one will survive, but this one will be 1. So we will have, therefore, so this basically, just so you're not confused, this is 1 minus 0. This one is 1, this one is 0 at t equals 0. So from here, we can conclude that this constant C2 is equal Q naught dot plus I omega Q naught. And now we can substitute C2 over here, C1 over here, and we have general solution for this differential equation. And then we will, of course, go back to x and y because we are interested in x and y components and find trajectory in the x and y directions. I will do that after I erase blackboard. So this is where the derivation in the previous part of the video finished. We have our variable q that is identically equal to x plus iy, and everything is function of time, of course, here. And that variable was in a differential equation that has this solution. We just found these coefficients. So what we want to do now is to express this differential, this solution in terms of x and y, but also we want to manipulate a little bit these exponential terms to write the solution in terms of sine and cosine functions. To do that, we have to know Euler's formula that says that E to some power I don't know, alpha is equal cosine alpha plus I sine alpha. This is one of the greatest formulas in mathematics and physics. Definitely something you should remember. So, knowing this formula, knowing that Q is equal this, we need to now plug that into this equation. So Q of t will be x plus iy, and I will omit function of time, knowing implicitly that everything is function of time. Q0, that will be x0 plus I y0 times this exponential function, and that would be cosine omega t minus I sine omega t plus this. First I will write this t so I don't forget it. That multiplies q0 dot. That will be u0 plus I v0 plus I omega q0 is x0 plus y0 plus iy0. So I will multiply immediately this with q naught that is written in terms of x and y. So I will have I omega x0, but here I would also have plus I squared omega y0, but I squared is negative 1, so it would be minus omega y0, and all that multiplies now this exponential term, and exponential term I again write it in this form. So that would be cosine omega t minus I sine omega t. Now, perhaps some of you watching this think, okay, now there is some trick to make this look nicer. There is no trick. You have to multiply these things. As Richard Feynman said in his second book on physics, sometimes you just have to do it. There is no tricks. You have to do the work. And the work is the following. X plus iy is equal. Multiply these. Let's see. That would be x0 cosine omega t minus I x0 sine omega t. Now these two plus I y0 cosine omega t, and now these two will be negative I squared, but negative I squared is positive 1. So it will be plus y0 sine omega t. Okay? Plus t that multiplies. Now I have to multiply these. So here I will have u0 cosine omega t minus I u0 sine omega t. Now this one multiply these two. Plus I v0 cosine omega t plus v0 sine omega t. Let me continue here. So I have now this third one. So that one will be plus I omega x 0 cosine omega t plus omega x 0 sine omega t. And finally, this one multiplies these two. So that should be minus omega y0 cosine omega t and minus I omega y0 sine omega t. I hope I didn't mess up some multiplication over here. Should I check it or not? Well, let's just proceed. The biggest issue is when you're multiplying, let's say, these two terms to make sure that I squared is -1 and so on. So, at any rate, what we will do now, we will find terms that are real on left side and the right side and imaginary on left side and the right side and match them. So that means that x, this real has to correspond to that real and this imaginary part needs to correspond to that imaginary part. And that means x is equal, so we have here x0 cosine omega t. So let's maybe do, I collected this term. This one is with the I. Oh, maybe at the same time I can write both. So y would be, for example, this term, minus x0 sine omega t. So we dealt with this term. This term is also has imaginary unit next to it, so it's associated with y. So plus y0 cosine omega t. So this term is done. But then we have this term without I, so it will go in the x component. So it will be y0 sine omega t. And now t, so the first one is also without any imaginary unit, so it will be plus t u naught cosine omega t, and so that is this one. Now we have this one, which is minus t u naught sine omega t. Some of you might say, oh my God, this is boring. This is beautiful. This is interplay between mathematics and physics. You follow mathematical rigor and you end up with solution of a problem that is purely physical. Think about it. That's mind-blowing. We further have t v0 cosine omega t. We collected this term. Now we have plus v0 times t sine omega t. We finished with this term and now we have this second row. So here we will have plus t omega x0 cosine omega t. That's this term. Here we have plus t omega x0 sine omega t. This term minus t omega y0 cosine omega t, this term, and finally this term will be minus t omega y0 sine omega t. Well, so basically this is the solution, but of course we will not leave it nasty like this. What we will do, let's write here, we will say that x as a function of time is equal. Let us collect all cosine terms. This is cosine term. This is cosine term. And this over here is cosine term. So next to cosine, I will have x0 I'll collect next one, minus t omega y0, that's the last one, and this one is plus t u0 times cosine omega t. Plus, let's collect the remaining terms next to sine. So we have y0. So we did this one. There is this one with associated with velocity. I'll put it at the end. And there is this one. So this one will be plus t times omega times x0 and this one plus v0t times sine omega t. And now we will do the same for the y component of this trajectory, collecting everything around cosine terms. We have this y0. Another cosine term is this one with the v, but I will forget for now about it. I'll take this one. So it will be plus t omega x0. So that's this term. And now we have also this term. And that is plus t v0. And that multiplies cosine omega t. Plus, now collecting terms around sine, we have this term over here, so minus x0. We have this one with the u component, that one I will put it third, and there is this one, so minus t times omega times y0, and finally I see now that there is a mistake here. Here it should be plus, because this minus and this minus will give me plus, which means that, which term is that? That is I omega y naught sine, I omega y naught sine omega t. Where is that? You see, when you're doing things live, you try to do this live. So because it's I, it has to be in the y equation. So omega y naught, so this should be plus over here, but that also means, therefore, that this should be plus over here. And the last term next to sine is this one, minus t u0 sine omega t. And this looks a little bit messy, but it's absolutely beautiful, is the solution for our problem after many minutes of derivation. So this set of equations gives you trajectory of this particle on a rotating disk. Disk is rotating with angular velocity omega, and the motion is restrained on the plane of this disk. Notice that you can check this equation setting omega equals 0. If omega equals 0, that means disk is not rotating. That means this term disappears. Sine of 0 is 0. This term, cosine of 0 is 1. This disappears. You get x0 plus tu0. That's the basic equation of kinematics for trajectory in the x direction, high school physics. Let's see y component. Again, if omega is 0, this disappears because sine is 0, cosine is 1. This disappears, omega is 0, you get y0 plus t v0, and that's again basic equation for kinematics of motion in the y direction. So we can see that motion on a non-rotating disk is simply a special case of the motion on a rotating disk when the disk is rotating with angular velocity omega. The only two forces that we considered were centrifugal force and Coriolis force. Of course, we neglected friction. If you introduce friction, this becomes exponentially more difficult, as always when it comes to friction. Now, you might say, can you tell us what is the nature of the trajectory described by these equations? The answer is yes, I can. The trajectories tend to have spiraling form. So if this is the initial location of the particle on some disk, and it has initial velocity like so, then let's say this is that entire disk that is rotating, let's say in this direction, angular velocity omega. Then the motion overall will be something like this, spiraling motion outward. That's the combination of centrifugal and Coriolis force. Coriolis, because this is counterclockwise direction, Coriolis force tends to deviate this towards the right. So you would go in circle, but you don't go in circle because you have also a centrifugal force that is pushing this out. So you have force that is pushing motion out and something that is constraining it to the right, and you get this spiraling motion. Now how fast this spiral spirals, of course, depends on many things. Depends on omega, depends on velocity. If you have very high velocity, then Coriolis force is not so strong, and you get you get maybe something like this. I hope you can see it. So spiral would be larger, or rather, if this is the end of the disk, the particle would leave the disk before spiraling too much. Why is that? Let's think about that. Because Coriolis force depends on the distance and time over which the force has time to act. So if the velocity is very high, well, this, and what does it mean very high? Well, very large compared to omega. That means that this particle would traverse this radius of the disk before Coriolis force has enough time to act. So this spiral would be very small. If the Coriolis force is very strong by introducing small velocity to the particle, this spiraling would be much, much larger. Of course, you can code these equations in a computer code, let's say MATLAB, and get these trajectories on your own. Here we have a very simple code that is analyzing the trajectory of a point particle on a rotating disk. We specify angular velocity of the rotating disk and initial position of the particle, which can be any position what you want. We will analyze two different initial velocities, and in both cases u component of the velocity is the same, but v component has the magnitude of 1 or 2 meters per second, two different cases. And we will investigate the motion of this particle over the time period of 1 second. Here are the equations that we just derived on the blackboard, and if I run this code now, notice that there are two lines. Red line or red spiral corresponds to higher initial velocity of the particle, 2 meters per second. Black one is 1 meters per second. The red one is wider in terms of spiraling motion because Coriolis force is weaker when the velocity increases. Coriolis force has less time to act. If we now, let's say, investigate the motion of this particle over a time period of 10 seconds, you will still see the spiral, but notice that the red spiral is way wider and particle advances far more radially from the initial position than in the case of the black line, once again because black line has lower velocity and therefore Coriolis force has stronger influence of the motion of this particle. Here we have a rotating table and camera that is attached to this table, and it is rotating together with it. Because camera is rotating, it is a non-inertial reference frame. And the video from this camera is projected on this TV over here. First, let us test if the table is horizontal. So we can see if I place this marble, the table is pretty horizontal, the marble doesn't move anywhere. Otherwise we would have the problem of gravity affecting our results. But I would say that the table is pretty horizontal. Lastly, I placed my mobile phone above this rotating camera. Unfortunately, I don't have another phone to record this entire setup, but you can conclude that my mobile phone is sitting above this camera. Camera is rotating, that means it is non-inertial reference frame, but my phone is static, that means it is inertial reference frame. Now we can take a marble and roll on the surface of this desk, which is basically a rotating disk. Oh, look at this spiral, look at this spiral. Oh, beautiful. One more time. And this is how you solve this problem. Until next video, goodbye.